Okay, so as some additional homework D2 help, I just wanted to do an example where we invert a kind of interesting looking CDF and make sure that everybody's sort of straight on how to set up the ranges and how to deal with these inverting functions, which are pieces of non-invertible functions, and so it creates some ambiguity in how to choose the like negatives and pluses and square roots and those sorts of things. And so let's consider a CDF of the form f of x is equal to 0.5 e to the x for x less than 0 and 1 minus 0.5 x minus 1 squared for x between 0 and 1, and then 1 for x greater than 1. And I'll just make the convention that the greater thans are the equals. Okay, and I guess I could just make this range, I'll just put the negative infinity in that range just to be explicit. Okay, so then what does this function look like? It's always good to get an idea of what you're about to deal with by plotting. And so we know that if we look at this, regardless of which branch we do f of 0, we know that f of 0 for this thing is equal to 0.5. If I plug in a 0 into here, I get 0.5. If I plug a 0, I'm sorry, when I say here, I know you guys can see that when I plug a 0 into the top line, I get 0.5. When I plug a 0 into the bottom line, I also will get 0.5. So f of 0 is equal to 0.5. So I may as well, make maybe I'll make this 1.0. So then somewhere down around here, this is 0.5. And then if I think about the shape of 0.5 e to the x for the negatives, it just looks like this. Kind of this decaying exponential on this side. And then if I were to plot the shape of this 1 minus 0.5, x minus 1 to the squared, it will go up to, well, so this only goes up to 1. So I'm going to plot, or say this is 1. And I know that after 1, this thing is all 1. And in between there, it rises and then falls off this way. So we have this kind of convex shape on the left and this concave shape on the right. And so that is our f of x. And so we'd like to invert this so that we get an f negative 1 of r. So by inverting, just so everyone's clear, basically if we think of these axes as an x-axis, so if we think of these axes as an x-axis and an r-axis, so r is equal to f of x, then all I'm doing when I'm inverting is I'm just flipping them along this diagonal line so that I instead, so I'm just sort of swapping the x and the y axes. So I'm just swapping these by folding them around that so that I get the r on the horizontal axis and the x on the vertical axis. And so after inverting, then that's the picture we have. And so so if I were to say that this function is r is equal to f of x, then the function that I'm looking for coming out is x is equal to f negative 1, f inverse of r. And so that is going to be some function that has ranges. And so it's got a range, it's got two ranges because there's two meaningful ranges up in the CDF. And I say they're meaningful because I really only care about the ranges of CDF where things rise from 0 to 1. So when they rise from f is equal to 0 up to f is equal to 1, those are the ranges that I'm going to worry about inverting. So this other range down here, I don't care about. I don't need to worry about inverting that because f of x is equal to 1 has already been taken care of by this kind of orange range. So these two orange ranges are the ones that I'm kind of worried or interested in down there. So if I were to pick this top range, then this is the range where x goes from negative infinity to 0. So my question is, what is the range of r here? Well, if I plug in a negative infinity into 0.5 e to the x, that is just going to give me a 0. And if I plug in a 0 into 0.5 e to the x, then that just gives me a 0.5. So the range of r that corresponds to this range of x is 0 to 0.5. Now that 0.5, I could have cooked up an example where the breakpoint wouldn't have been 0.5. So that won't, even though a lot of examples from the book are going to have 0.5 as that kind of special breakpoint in this R, that's not always the case. And so I try to make the homeworks a little bit harder than that. So look for breakpoints other than the homeworks, or other than in your homeworks, and then also, maybe in the exams as well. So don't always expect that R to go from 0 to 0.5. It might go from 0 to 0.2, 0 to 0.7. It could break at other times, and there might be there might be two breakpoints, so 3 pieces, or 4 or 5 or something like that. But for this example, it just happens to break at 0.5, meaning half of the mass is on the kind of left side of the function under the exponential, and the other half is under this quadratic. Okay, so then I'm interested in what is the other range of r. So now I look at the other range of x. So I'm now focused on this range of x. So when x goes from 0 to 1, what does r do? Well, when x is equal to 0, if I plug into this thing, then I find out that r, if x is equal to 0, then r is equal to 0.5. And if x is equal to 1, then r is equal to 1. And so that is my range. And so, and this is kind of what I meant in the orange case for meaningful, because my inverse function now sweeps all the way from 0 to 1, I've kind of done everything. So I just need a mapping from r between 0 and 1. I don't care about r outside of 0 and 1. There's no r's that are interesting to me less than 0 or greater than 1. R is going to be a uniformly distributed random number between 0 and 1. So once I've gone from 0 to 1, I'm done. So then all that's left now is me to figure out what are the forms for these two. So this we can call case 1, and we can call this one case 2. So case 1 will be the exponential, and case 2 will be the quadratic. And we can invert them separately without having to really worry about the two of them. It's not like when we're taking the integrals. So I'm just going to flip to another page here and consider case 1. And so case 1 is the case when x is, let's say when x is between 0 and negative infinity, and r is between 0 and 0.5. And so we know that in this region, big F of x is equal to 0.5 e to the x. And so if I were to set r equal to 0.5 e to the x and solve for x, then I get 2r is equal to e to the x. If I take the natural log of 2r and the natural log of e to the x, then I get the natural log of 2r out on one side and just plain old x on the other side. So that is the answer that I was looking for. X is equal to the natural log of 2r, and that again is for 0 is less than r is less than 0.5. So if I were to plug in a 0 into here, well, the natural log of 0 will give me x is equal to negative infinity. And then if I were to plug in a 0.5 in here, well, the natural log of 1 will give me x is equal to 0. So this properly maps 0 to 0.5 to negative infinity to 0. So that checks. These two things both check out. So I think I did case 1 correctly. So now let's look at case 2. So what is case 2? This is when x is between 0 and 1, and r is between 0.5 and 1. And for this case, f of x is equal to 1 minus 0.5 x minus 1 squared. If I set r equal to that, and then I end up doing a little bit of arithmetic, then I can get 0.5 x minus 1 squared is equal to 1 minus r. So x minus 1 squared is equal to 2 times 1 minus r. So then x minus 1 is equal to plus or minus, I don't know which one yet, 2 times 1 minus r. So then I complete everything and I get x is equal to 1 plus or minus square root of 2 times 1 minus r. And so the question that I have is, what value do I choose, plus or minus, in this case? Well, all I need to do to figure that out is look at these ranges. So for this range up here, 0.5 to 1 in r, if I were to then plug that in, I say, well, then 1 minus r, if r is between 0.5 and 1, then 1 minus r is going to be between 0 and 0.5. And then 2 times that is going to be between 0 and 1. And then so the square root of that is going to be between 0 and 1. And then so basically I'm saying that I have two possibilities. X either is 1 plus some value between 0 and 1, or x is equal to 1 minus some value between 0 and 1. Well, what do I want? Well, if I look back up here, I want x to be between 0 and 1. But if I look down here, this one here would give me an x that's always greater than 1. So that is wrong. So that means that this must be the right answer, which means I should choose a negative, which means for this case, x is equal to 1 minus square root of 2 times 1 minus r. All right, so this just happened to turn out to be minus. In other examples, it might equal plus. You just have to check that based on the input range of r, what do I need, plus or minus, to get the particular output range of x. So I can put all of those things together, and I then get an inverse function. So if you want, you can say not r. You can say that my inverse function, if you want, you can put the x equals. It doesn't matter too much to me, but f is equal to f inverse r in these two regions. And so that first function for case 1 is natural log of 2r. And that's for 0.5 is less than r. Oh, sorry. It's for 0 is less than r is less than 0.5, and I'll just make that less than or equal to, and maybe that less than or equal to. And then for the top half, that's case 2, which is 1 minus square root of 2 times 1 minus r, and that is for 0.5 less than r less than or equal to 1. And that is our inverse transform generator for this PDF. And if you notice, the input to this function, so r, that is always going to be between 0 and 1, but the output here will be between negative infinity and 1. And that should make sense. Why should that make sense? Well, if I go back and I look at the CDF here, so the plot of the CDF, you can see that it is totally flat in this region over here. It never rises, which means that I'll never get any outcomes over here. So when a CDF is flat, that means that there are no outcomes in that region. So the only region where the CDF is not flat is, I guess I've sort of used up, well, I'll do orange, that actually fits well, is this region. So this is the only region where the CDF is not straight, totally flat, and that's the region where x goes from negative infinity to 1, which is why our inverse transform generator over here goes from negative infinity to 1. So it is matching that. It's able to bring in numbers that come from, say, Microsoft Excel that are from 0 to 1, and then turn them into numbers that are from negative infinity to 1. You don't need to play with the ranges of the incoming random numbers. You just leave them between 0 and 1, and then this function will then magically turn them into the proper negative infinity to 1. And so I don't know if it helps, but then let's also just take a look at what the PDF of this thing might look like. So I'm just going to lasso this CDF here and bring it over. So if I were to say, I'll just paste that CDF here. If I were then to derive the PDF, then when you take the derivative, when you integrate to get the CDF, it's complicated, but when you take the derivative, it's pretty easy. So when you take the derivative, then the derivative in the first region is just going to be 0.5 e to the x again. That's just the derivative of e to the x is e to the x. So that is for all the negative values of x. And then if I were to take the derivative of this this other thing here, then so this is a little uglier. So I guess I can leave it in that form there. In which case, I would get a minus 0.5 times 2x minus 1. And so that turns into minus x minus 1, which is just equal to 1 minus x. So the derivative, so this, what I can do is, now I've done that kind of work in place, I'm just going to move it somewhere else. So I'll just move that over here, and maybe I'll just circle that, and I'll just put a 1 minus x here, and that is for 0 less than or equal to x less than 1. And so I'll just point. And then the derivative of this last one is just equal to 0 for x greater than or equal to 1. And so that is my PDF. And so if you were to then run all of those uniformly distributed random numbers through this function in Microsoft Excel, then it would spit out a bunch of numbers that would, if you took their histogram would look a lot like this thing down here, where the histogram would be, it would be, if I were to sketch it out, it would look, well, maybe we can just sketch it out on the next page here. All right, so obviously this isn't this. All right, let's try that one more time then. All right, well, so what I was trying to get is if I just plot this thing, so I'll go on to the next page here, and if I plot, so I'll just flip back, and if it's this, it'll look similar to the CDF on the negative side, and then on the PDF side is just 1 minus x. So, which will end up looking like this. So this is me just trying to make this line darker. So, well, that's pretty ugly. Let me just. So I could put a, say, a 0.5 around here, and I could put a 1 somewhere up here, and once I got down to 1, then this thing would get back down to 0. So I'll draw a straight line here, and I will draw a little curve down like something like that, and it will be 0 outside of here, and I'll just highlight these guys. And then so in Excel, if you were to generate a bunch of these numbers and take their histogram, then you should get a histogram which sort of etches out this shape. So something along these lines. All right, well, I guess I didn't have to fill those in, but yeah, so you get a histogram that looks kind of like this. And so you would get no values, you would get a very few values out in this region. So that's very few. And you would get none in this region, and then most somewhere around here, and you would definitely get this kind of jump. And so that's what that would look like. And so what would the coding look like in Excel? Well, if you look back at this form here, this inverse transfers function that we wrote, then how do you implement that in Excel? You just remember what it looked like. And in Excel, you'd imagine having imagine having like an A column and a B column, and in your A column, so like let's say this is an A column row 1, you'd have equal rand, and then you then can just fill that down for many, many lines. And then your B column, in order to implement the inverse transfer function, you can just have an if function that says if A1 is greater than 0.5, then you implement this function using Excel. And then otherwise, if it is less than 0.05, you implement this function in Excel. And then, of course, if we had multiple branches here, if we had 3 branches or 4 branches or whatever, then in the false sides, you could then do a bunch more ifs, a bunch of nested ifs to implement all of the other branches. And then you just take that and you fill down, and the histogram of the A column will just be a uniformly distributed random number, so it'll be uniformly distributed between 0 and 1, and the histogram of the B column will be that one that we just drew, where it looks kind of like that. There's 0, it's something along those lines. So that's basically in a nutshell how you would invert this and then run numbers through it in Excel.